In this video, we're going to go ahead and cover section 4.6, graphs of other trigonometric functions. This is still unit 4, trigonometry. Okay, this one is pre-done just because there's a lot of graphing, so I didn't want to spend too much time in the video actually drawing the graphs out. So here it is. The first function we're going to see that's different besides sine and cosine is the tangent function. This one is also in your foldable in the same tab where you have cosine and sine. And you'll notice that it has a very different look. Okay, so this one looks like a bunch of repeating curves, kind of like a cubic function almost, but it has asymptotes at every interval. So we actually have an interval of pi between each asymptote where you have, so if you think about it, this is pi halves is equal to 1 pi. So every pi after pi halves is going to be a vertical asymptote for our parent function of tangent x. And basically in between, we have this weird looking curve repeating forever. Okay, so here are some of the characteristics that are important. A lot of stuff to copy on this first page. We have that the period for this one is pi because like I showed you, you have that pattern going on between an interval of pi. And don't forget that n is going to be all in an integer, which we mentioned in the previous video, just for reference. The domain is all real numbers except for those asymptotes. So at pi halves, we have a vertical asymptote, and every n pi plus that is going to give us an asymptote. So if I do pi halves plus 1 pi, I have an asymptote. Pi halves plus 3 pi, I have an asymptote. And that's what this is referring to as far as where it's not defined. Okay, so another way to write this is x is not equal to these values because again, we have vertical asymptotes where it is undefined. The range is going to be all real numbers because even though we do have those breaks, this curve, the curve that's going up and down, goes on forever. So it's all real numbers. We already said this, repeating that. Intercepts are every n pi. So if we look back at our picture here, we have an intercept at 0, we have an intercept at pi, negative pi. So basically every pi, 2 pi, 3 pi, 4 pi, and the same on the negative side, we're going to have an x-intercept. Okay? Y-intercept, we just have the 1, 0, 0. This one does have odd symmetry, and you can tell just by looking at it, it has that kind of diagonal symmetry. Okay. The key points for this one, unlike the cosine and sine, are going to be your intercepts and your asymptotes. So for the ones before, it was the intercepts, the mins, and the maxes. This one's going to be the asymptotes. And this one is going to use kind of a starting point, ending point type of deal that I kind of mentioned in the other video. In the other video, it's a little bit easier, I think, to just kind of move things around based off of our OG. But for this one, because we have so many undefined places, we're going to actually find two consecutive vertical asymptotes. And we do that by using the following little formula. Bx minus c is equal to negative pi halves. So that's kind of like the first side. And then bx minus c is equal to positive pi halves. That's the second asymptote. And these two are together. So if you can find one pair of asymptotes, well, the curve just lies between it. Okay. This is also going to be equal to the period because it's the distance between those two asymptotes. To kind of show you where this is coming from, you will see that we have our general form here for a tangent function, y equals a tangent of bx minus c. And we could add a plus d at the end if we wanted to, but we're going to focus mostly on this form for this set of notes. So let's go ahead and try some of these, or at least look at some of these. We have, for example, number 1, okay, to sketch the graph of tangent of x over 2. So I have these kind of color coordinated with the steps. The first thing we're going to do is find two consecutive asymptotes. And to do that, we use the little formulas that I showed you. Okay, so we're going to go ahead and do bx minus c is equal to negative pi halves. It's like the left side. Bx minus c is equal to positive pi half. That's the right side. This part is the part that's inside the parentheses. So in this case, it would be x over 2 is equal to this, and x over 2 is equal to positive pi halves. If you solve these, you'll see that all the 2's kind of just, they come out to a 1. So we're left with x is equal to negative pi, and x is equal to pi. Okay, and basically these are going to be the asymptotes that we're looking at. Okay, so the period always lies between these 2 points. So if you think about it, negative pi and pi, that's a space of 2 pi. So let's go ahead and write that in here on the period. This is going to be a period of 2 pi because from negative pi to pi, you have to cross over the 0 and then go over to pi, which is a space of 2 pi. Okay, so we have the first part. Step number 2 is to make a table so we can find some of the x-intercepts and possibly other points in between just to kind of have a better idea of the sketch. So that is what I did next here. Okay, so let me explain this a little bit first, just so we can kind of see where all these values came from. Negative pi is my first point that I'm looking at. Pi is the last point that I'm looking at. And just while we're here, before I move on to anything else, there will be a VA at every pi plus n. So at every integer after this, we're going to have another asymptote. Okay, so let's go ahead and look at this part right here. This is our function. So basically all I have to do is take my x and plug it in, which is what you see here, tangent of negative pi halves. Okay, how do you find the value for this? Well, I mean, we do have a handy dandy little foldable. Okay, so let's look at pi halves. In this case, tangent of pi halves. So if I know that pi halves is located at the, I mean, I guess I can look at any one of these because all of these have pi halves, right? This is positive pi halves. Remember that negative pi halves is on the other side. So this point right here is actually negative pi halves because remember we go backwards for the negatives. And at negative pi halves, we have that tangent is y over x. So it would be negative 1 divided by 0. And negative 1 divided by 0 is undefined. Okay, so that's where that first one is coming from, undefined. The second one, we're going to go ahead and plug in negative pi halves into my x. So negative pi halves divided by 2, this actually comes out to negative pi fourths. Okay, so now we're going to look at negative pi fourths. So let's find my pi fourths. It's over here. Remember again that the negative values go clockwise. So negative pi fourths is going to be this piece right here. And again, we're doing the y divided by the x. They happen to be the same number, so it's like saying negative this divided by positive that gives us negative 1. And that is where I got this negative 1 from. And it just kind of follows through with the rest. So tangent of 0, we look at 0. All of these have 0, so I could just look at the 0 right here. Y over x, so 0 divided by 1 is 0. Tangent of pi fourths, and I'm getting the middle value by plugging in this number into the x. Okay, so tangent of pi fourths is going to be this guy over this guy, which is also just positive 1. And then we have undefined for the last one. Okay, so with those values, I can go ahead and kind of do a sketch here. We know that at negative pi, it's undefined, which it should be because that's where we have a vertical asymptote. Okay, so there's one vertical asymptote. We also have it undefined at pi. That was this one up here. And again, that should be right because we found that this was a vertical asymptote up here. Okay, so there are my two consecutive vertical asymptotes. I have a point at 0, 0. So this point 0, 0 is right here. And I have a point at negative pi halves, negative 1. So negative pi halves, negative 1 is right here. Positive pi halves and 1, that's right here. And we can draw our curve. And based on this one period of this function, I can kind of, you know, figure out where the rest of them are going to go. You'll notice that since it has a period of 2, well, if the asymptotes are spaced apart 2 pi's, the intercept is also spaced apart 2 pi's. So it'll be 0, 2 pi, negative 2 pi. Okay, that is about it for this one. I think I did have one note right here that says note that this is a horizontal stretch. If you compare it to the original, you're going to see that it's pulled apart horizontally. And that does make sense because remember that when it comes to transformations that are inside the parentheses, it's always kind of opposite of what you think. So instead of it being division, we actually kind of multiplied it to make it, wider. Okay, and that is it for this example. Here is example number 2. It says sketch the graph of -3 tangent of 2x. Okay, so we added another number in the front just to kind of mix things up a bit. We also made it negative. So keep in mind that a negative is a reflection over the x-axis. So this one, remember our tangents kind of do this, right? This one, you can't see that, kind of does that. A reflection is going to flip it. So this one's probably going to be the other way, kind of like that. Let's just keep that in mind, okay? Let's start with the first step, which is to find two consecutive asymptotes. We do that by setting bx minus c, which is the inside, equal to negative pi halves, and then also to pi halves. So that is done right here. My inside is just 2x, so 2x equals negative pi halves, 2x equals positive pi halves. If we solve this, we basically we divide both sides by 2. So if I divide this by 2 and I divide this by 2, or multiply times a half, think of it that way also, we get negative pi fourths. Same thing on this side. If you divide this by 2 or multiply it by a half, okay, we get pi fourths. So the period for this one is between negative pi fourths and pi fourths, which is the span of 1 pi. And if you're not sure how I'm doing this, you can also think of it like this. Take this guy right here, pi fourths, and subtract whatever this is, negative pi fourths. Okay, so that's going to give us, let's see, plus it's going to give us 2 pi over 4. Oh, actually, you know what? It's a good thing we did that, because look, I was wrong. It's actually pi halves. So the period's going to be pi over 2, not pi. See, so you always want to check just in case. I did that on purpose, just to show you. All right, so the period's pi halves. We're going to go ahead and subdivide even smaller on our step 2. So step 2 is to go ahead and make a table. So I take my vertical asymptote. So there's this one and there's this one. And you always want to have at least 3 points in between. So the best way to do this is just to kind of divide it by 2. Pi fourths divided by 2 is going to give me pi eighths. So that's where I kind of got these numbers from. Okay, and we do the same thing we did last time. Now here, there's a lot of algebraic work that goes into this part. So I'm not going to go over every single one, but I guess I can go over at least one of them. If we look at the first one, -3 tangent of 2 times negative pi fourths. Okay, well, this right here, I guess I can kind of just, let me do a little bit of side work. I will do this one. I'm not going to do all, I'm going to do just one. So this would be -3 tangents, okay, of -2 pi over 4 is the same as negative pi halves. Okay, so you're thinking, let me find what this is first, and whatever that is equal to, multiply it by -3. Well, based on what we saw from the other one, we know that at negative pi halves, remember, negative pi halves is down here. This is going to be undefined for tangent, because -1 divided by 0 is just, you can't do that. So it's undefined. So right off the bat, you don't even have to worry about the -3, because it's undefined. Okay, if we do, I'll do one more. If we do this one right here, this is going to be negative pi over 4, because this one simplifies, right? 2 over 8 is 1 over 4. So we would be looking at, again, this is pi fourths. We're looking at negative pi over 4. So we'd be looking at these values right here, which is going to be this divided by this, y over x, which is going to give me -1. Okay, because this part right here divided by the same thing is 1, but since it's negative, it's -1. So you essentially have -3 times -1, which is +3. And that's how we got the rest of these values as well. So we can go ahead and use those values to plot our graph. The first thing you want to plot are the asymptotes, so negative pi fourths and pi fourths. There we go. Okay, and we have an intercept at 0, 0. We have a point at negative pi eighths, 3, and a point at pi eighths, -3. And this seems to make sense because, well, this was a reflection, yeah? So this graph should be the other way. And we could fill in the rest. Let's go ahead and do that real quick. And there we go. We went ahead and just did 2 more iterations of this. You can see that since this space right here is pi halves away, this is also pi halves. If it helps, you can also kind of count. There's 4 little spaces. So 1, 2, 3, 4. There's our next asymptote. 1, 2, 3, 4. There's our next asymptote. Same with this guy. This is just in between those. So this one should be in between those as well. Okay. Couple notes here at the bottom. We have that since a is -3, we have a reflection over the x-axis, which is what I mentioned. That's why this one is kind of going backwards. And a horizontal shrink, because b is greater than 1. The horizontal shrink is kind of hard to see because we also have a vertical stretch. So don't worry too much about these. If you know, let's just kind of go into a little bit into transformations there. But essentially, what happened here, since we have both a stretch on the outside and a shrink on the inside, they kind of nullify each other out, sort of because they're different. They're different numbers. But like I said, don't worry too much about that. For these, I would like you to please at least show me this part right here. Show me your table. Show me how you found the asymptotes, and then show me your graph. Okay, let's go ahead and move on to the next example. We have covered tangent, and now we're going to cover some of the other ones that you've seen. Cotangent is the first one. This one is basically the reciprocal of tangent. So what happens is it just kind of flips, yeah? So recall that this is equal to this, which is cosine over sine. So this means that the x-intercepts are when this is equal to 0. And this happens at these values. Okay, so if you look at your little unit circle, you'll notice that at pi halves, 3 pi halves, where tangent used to be undefined, okay, this one is equal to 0, and vice versa. So you'll see that our graph kind of does the opposite thing here. Okay, to kind of give like a better visual, let me show you the other foldable, the one that has like a whole bunch of stuff, and show you these two next to each other. So here is cotangent. Okay, let me kind of move this over. And then here is tangent. So you'll notice that tangent is centered in the middle, right, between negative pi halves and pi halves. And this one is not. This one is centered outside of the origin. Why? Because, well, while tangent is undefined at these values, cotangent is undefined on the opposite values. So the intercepts and the VAs, they just swap places. Pretty cool. All right, let's look at some of the properties of this, and then we'll go ahead and move on to an example. A lot of the rest of this set of notes is just a lot of copying. Okay, so we have some properties down here again, and it's just an integer where the period is still pi because that doesn't change. The domain is going to be everything except for those pi's. So wherever you have a pi, 1 pi, 2 pi, 3 pi, that's where you have the asymptotes now. Okay, which means that the domain is everything except for those. Range is still our real numbers. My intercepts are now what used to be the asymptotes for my tangent function. So pi halves plus and pi comma 0. This one also has origin symmetry, just like the one before. To find the asymptotes, we still do the same thing, but now instead of using pi halves and negative pi halves, we're going to be using 0 and pi because that is where our asymptotes are located. Okay, so let's go ahead and try an example. And actually, no. This one I'm not going to do an example for. We'll probably do something similar in class. We're going to move on to the next reciprocal function. Cotangent was the reciprocal function of tangent. And this one is the reciprocal of sine. Okay, so we have cosecant, which is 1 over sine, where this cannot equal to 0. Because we have a place where it cannot equal to 0, where it's undefined, this one also has vertical asymptotes, which is kind of weird because I know sine doesn't, but maybe the picture will kind of help. Okay, if you notice this part that's like lightly put in pink, this is my sine function. Since this is the reciprocal, well, all it does is it flips. So this curve goes upward now, this curve goes downward. And what used to be a maximum is now a minimum, and vice versa. So really, really weird looking stuff going on, kind of like a weird looking basketball court, right? Cosecant looks like this. The period is still 2 pi. The domain is everything except for where we have x-intercepts on sine, so 0, pi, 2 pi, basically any pi. Um, the range is going to be everything except for uh, everything that's between -1 and 1. So if you notice, there's like this big gap here in the middle. That's because that is where sine was originally located. And since we're flipping this, we have nothing in there. So it's everything from -infinity all the way to 1, sorry, -1, and then from 1 to infinity. There's no x-intercepts because, again, that part is taboo. And this does have odd symmetry, believe it or not. If we were to do a rotation 2 times or a double flip, this pattern continues, you'll have these kind of matching up together and so forth. So let us try an example. This is one that I kind of have a interesting way of showing you. We're going to sketch this function, y equals 2 cosecant, is it x minus? Yeah, x minus pi fourths. So make sure that this is a minus, okay? The first thing I do for this one, I have this one in pieces because I just think it's a little bit easier to show, is I went ahead and did my OG. So you can see that my OG is the one that is, dashed. And the reason I chose sine is because to graph cosecant, it helps if we have sine. Because if we have sine, all I got to do is kind of do like a little flip, and that will give me cosecant. Okay, so here is y equals sine of x. It's the dashed one. And what I went ahead and did is I'm going to go ahead and do the pi fourths first. So sine of x minus pi fourths. This means pi fourth spaces to the right, or a phase shift to the right. So you can see that I did that here. I took all my points and I moved them over pi fourths. So that went over, this one went over, and so forth. You saw everything just moved over to the right. Okay. Then I went ahead and added something else to it. So on my next little page here, like I said, cool little booklet here. On my next little page here, I went ahead and did 2 sine of x minus pi fourths. So now I'm going to go ahead and put that 2, which is the next part, okay? And we know that a 2 in the front is an amplitude of 2, which means that it's a vertical stretch by 2. So all of my points that I had on the previous page, the green one here, I'm going to move it up to the 2 point, because it gets multiplied by 2. 1 times 2 is 2. -1 times 2 is -2. And this now represents my 2 sine of x minus pi fourths, okay? And we're almost done. Once you've gotten to this point, well, now we're ready to go ahead and do the cosecant part. Cosecant is basically just flipping all this out, right? So my last step here is to do that. And hopefully you can understand this graph. The pink part is what I had on the previous one, okay? So you'll notice that my graph, all I did is I made a curve on top of this one, a curve below this one, on top, below, and I even labeled the points where we have our asymptotes. So our asymptotes are wherever my x-intercepts were. So here, -3 pi fourths, pi fourths, what is this? 3 pi, I'm sorry, 5 pi fourths, 7 pi fourths. I should probably label that one. 5 pi fourths, okay? And that is basically where my asymptotes are, okay? I went ahead and just put a few notes here that a equals 2 and pi fourth units to the, forgot to write this down, to the right. Yeah, I think I probably wrote something else. That's why I crossed it out. But yeah, so yeah, that's basically it. That's another way we can do this kind of problem. Um, Hopefully that helped a little bit better with the visuals. Okay, let's try another example. I think we're going to go ahead and do the next type of graph. This was cosecant. So next we should have secant. Let's see if that's next. Yep, we have a secant graph. And just like I mentioned earlier, maximums become minimums and vice versa. This one is going to be your reciprocal of cosine. So secant of x is 1 over cosine. Again, this denominator cannot equal to 0. So where cosine is equal to 0, that's where we have our asymptotes. And it basically works the same way as the one before, except now we have, the graph is shifted over just a little bit. So period's the same, 2 pi. Our domain is everything except for wherever we have those vertical asymptotes. So every pi half plus a pi. That's where we had our zeros on cosine. Range is the same as before because, again, this middle section is a taboo area for these reciprocal functions. Intercepts, we have one at 0, 1. And symmetry is this, for this one is going to be even because we have that flip over the y-axis going on. So just like the one before, okay, and I kind of, this one's all over the place, but for the one before, we're going to go ahead and do like a double sketch. This is what we're doing, y equals secant of 2x, okay? So what I did first here is I went ahead and graphed cosine of x, which is the dotted one, because remember this is the reciprocal of cosine. So there's cosine. And what else did I do with this one? Okay, yeah, and I went ahead and did y equals cosine of 2x because that's what's going on here. So for y equals cosine of 2x, we kind of have to mess, that's the one you have to mess with the b with. You have to find our period, which is 2 pi over b. So 2 pi over 2 gives me pi, which means that instead of it being between 0 and pi here, okay, I'm sorry, 0 and 2 pi, we're going to have to kind of squish it in, okay? So I went ahead and did that, and I got these 4 spaces between, okay? So between 0 and pi, we have kind of like this, 1, 2, 3, 1, 2, 3, 4. So pi 4 is pi halves, 3 pi 4 is a pi, and this becomes my new curve. Okay, if that didn't make any sense, I also kind of did a table up here. I think that's what I might have done the first route. I said the period's going to be 2 pi over 2, so it's a horizontal shrink, and I kind of did my values here. So between 0 and pi, you plug those values in, and these are the numbers that I get. Okay, so that's where I got like these values from. Okay, so from there, I went ahead and just translated this onto this graph down here. Ignore the black part, I kind of messed up there. And basically this pink part right here is what you saw over here. And all I'm doing is I'm taking the top of the curve and I'm putting a curve here, I'm putting a curve down here and up here. And wherever you have these intercepts, that's where I'm putting my vertical asymptotes. I did that backwards, didn't I? There you go, that's better. So asymptote, 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 curve, curve, and curve. And there we go. Okay. And that's it. That's it for that one. I think that might be it. Let me see if there's one more or not. Nope, that is it for this section, guys. So if you do need some more help with this one, like I said, please let me know.